topic of today's lecture is SAT solving. We met the satisfiability problem, the SAT problem, last week, and SAT solving is about finding algorithms for solving the SAT problem. And in practice, we don't just want algorithms, we really want working computer programs that we can use to solve the SAT problem. So let's write the topic, SAT solving. So that's the title today. So I'm going to start by reminding you what the SAT problem is. So this we did in last week's lecture. So the SAT problem. So this is an algorithmic problem that we want to solve. Like most algorithmic problems, we have an input that we give, and then we want the algorithm to go and find a certain solution and return the solution. So in our case, the input was a formula of propositional logic. So the input was a propositional formula. Oh dear, sorry about that, I pressed a button. Let's just get rid of that. So, propositional formula. It's a little bit painful with this tablet, but I'm sure we'll get used to it. So it's a propositional formula, but we saw last week that without loss of generality, we can actually ask for this formula to be in a particular form that is in conjunctive normal form. That is, you remember, a conjunction of clauses. And we saw that that can be asked for without loss of generality because we had the Satan transformation that transforms any propositional formula into a formula in conjunctive normal form with the property that the transformed formula, the satisfying valuations for it, are in one-to-one correspondence with satisfying valuations of the original formula. Furthermore, say that Satan transformation has another important property, which it's efficient to compute, which is that it's efficient to compute in that the Satan transformation only involves a linear blow-up in the size of the formula. So without loss of generality, the input can be a conjunctive normal form propositional formula. So that's a propositional formula in CNF, conjunctive normal form. And the output we want the SAT solver to answer the question, is the propositional formula satisfiable? That is, does it have a satisfying valuation? So the output, well, in the simple case of the problem, which is in any case still not simple, is that the output should say yes if the formula is satisfiable and no if the formula is not satisfiable. But often we want, or in fact almost always in practice, if we're using the SAT solver to solve a problem that we're interested in because we've translated the problem we're really interested in into a satisfiability problem, usually we don't just want to know that the formula is satisfiable, but we want the additional information of being given an actual satisfying assignment of truth values to the propositional variables in the formula, the propositional atoms in the formula, that is. And that's useful when we use a SAT solver to solve a problem from a different area that we're interested in, because often the satisfying assignments will give us the information we wanted to solve the problem. For example, if we look at the three colorability problem that we considered last week, the three colorability of a graph, then we translated that into a propositional formula, and it's the case that a satisfying assignment for that propositional formula gives us a three coloring of the graph. So we really need that assignment to get back the three coloring. We don't just want to know that a three coloring exists. So the output we want in general for the form of the problem we're going to consider is yes, it is satisfiable, together with, in this case, the additional information, that's a plus, together with, in this case, the additional information of a satisfying assignment. So yes plus a satisfying assignment. We get that if the formula is satisfiable. So if the formula is satisfiable, it's a bit messy, but I've said it clearly, and no if the formula is not satisfiable. And so today the goal is to actually consider algorithms for solving this problem. Okay, let's give ourselves a fresh sheet of paper, which I think I can do by going up here. There we are. Let's move to a fresh sheet of paper. Right, well, last week we learnt or remembered, if we knew it already, that is a difficult problem. And it's not just difficult, but we can say precisely how difficult it is. It is an NP-complete problem. That is as hard as any problem that can be solved in non-deterministic polynomial time. And as I reminded you last week, such problems we don't know if they can be solved in deterministic polynomial time. So they are thought to be inefficient problems, problems that have no known efficient solution. So for a long time, people thought that there was very little hope of writing practical algorithms for problems like the SAT problem, because it's very difficult to find and presumably impossible if P turns out to be different from NP. So it's very difficult to find a polynomial time deterministic algorithm, and certainly an efficient algorithm we're going to want it to finish in time normally polynomially bounded in the size of its input. But then around the turn of the 21st century, and from that time onwards, people started realizing that actually, even though there is this difficulty in providing an algorithm that works for all cases efficiently, that for many practical purposes, various quite efficient methods could be brought to bear on the satisfiability problem. And this led to the development of algorithms, which has been a flourishing activity for the last 20 years, and has culminated in the kinds of practical SAT solvers that are now available for use. And these can really work extremely well. So the kind of algorithms people use in practical SAT solvers nowadays, they're very elaborate and would require a whole course about SAT solving if we really wanted to get to the business of understanding such algorithms. So what I want to do today is just to look at one algorithm for solving the satisfiability problem. And this is actually a very, very old algorithm. So this old algorithm is no competitor at all for the modern SAT solving algorithms that contemporary SAT solvers run. However, it is the basis for many of those algorithms. So although this is an old historic algorithm that is not competitive by any means by today's standards, many of the current competitive algorithms are built on top of this old algorithm. So the algorithm we're going to look at, we can't expect it to be efficient in general, and it's not even going to be that efficient in many practically interesting cases because it's a very old algorithm. But nonetheless, it's still going to work quite well on the smallish examples that we're going to look at. So we give up trying to find a very efficient algorithm, and we're going to look at an interesting algorithm that is not bad and has some good ideas in it that are used in the basis that are used as the basis for the development of modern SAT solvers. So the algorithm we're going to look at we're going to look at a particular algorithm called the DPLL algorithm, after the names of the people who developed it. And that development was actually done in 2 stages, both of which involved Martin Davis. So the first stage was by Davis and Putnam, and it really is a very old algorithm, 60 years old. And then it was extended and improved by, again, Davis, Logika, and Loveland. And that was 2 years later. Right, so to see how the DPLL algorithm works, I'm going to first work through an example, and then, having run the algorithm by hand through an example of a formula in conjunctive normal form and found a satisfying valuation for that algorithm, I'm going to then give you the general algorithm. It's actually quite reasonably well described on Wikipedia, and off the course web page I will put a link to the Wikipedia algorithm on the DPLL algorithm. Anyway, you can easily find it by just searching for DPLL algorithm. Okay, so let's have a new page for running the algorithm. So if I go up to here, so we're going to run it on a particular input formula. And the input formula I'm going to write down here. I won't bother to put words with it. So the input formula, I'm going to use a certain notation though. So I'm going to use square brackets to, oops, that's given me let's delete that and try again to do square brackets. There's a button on the pen that I need to be, let's try and get rid of that. I think I've pressed a button on the, okay, that seems to be working better. Right, sorry for these problems to do with using the tablet. This is my first attempt at using a tablet for a video presentation. Right, so I'm going to use square brackets. Oh dear, it's done it again. Okay, but anyway, let's just carry on with that. That looks quite good. So I'm going to use square brackets to mark the start and end of the formula in conjunctive normal form, and I'm going to use round brackets to round brackets around the clauses. So here we have, let's make that a bit neater. So here we have the first clause. So the clause is P or Q, and not P, not P or R, and not Q or not R, and not P or Q or not R. And that's the end of the formula, of the whole formula in conjunctive normal form. So we'll put these brackets around, square brackets around. Now it's quite easy for you to see rather quickly, if you try, that this has a satisfying assignment. It could also easily be solved using a truth table and just checking for a row in the truth table that has a true as the value of this formula. That's easy because we have 3 propositional atoms here. Actually, when one's sat solving, one normally talks about propositional variables rather than propositional atoms. It means the same thing, or often one simply says variables. So I might from now on say variable rather than propositional atom, at least sometimes. So because we've got only 3 variables in this formula, then we've only got 8 rows in the truth table, so it would be really easy to check. So one measure of the complexity, or the difficulty, if you like, the potential difficulty of a formula that you give to the SAT solver is the number of variables it contains. Because if we're trying to solve using a truth table, if we had n variables, then we would have 2 to the n rows, so we have an exponential blow up in the number of cases we have to check in the number of variables. So the number of variables is a very important factor in SAT solving. Of course, SAT solvers try to avoid the exponential blow-up as far as they can. The other measure of complexity is the number of clauses in the conjunctive normal form. So here we have a formula with 3 variables and 4 clauses. And we're going to run the DPLL algorithm on this formula. So what does the DPLL algorithm do? Well, the first thing it does is it checks to see if there's anything called a unit clause in the formula, in the conjunctive normal form. A unit clause is a clause that contains only one literal within it. So in this case, we've got 4 clauses, the P or Q, not P or R, not Q or not R, and not P or Q or not R. None of those have only one literal in, so we have no unit clauses. So we then go to the next stage of the algorithm, and the next stage of the algorithm says, let's see if we have any pure literals. What's a pure literal? Well, a pure literal is one that occurs either only unnegated within the whole conjunctive normal form or only negated within the whole conjunctive normal form. So P is not a pure literal because we have P here, and then for it to be a pure literal, we would have to not have not P occurring anywhere. But we do have a not P, so it occurs both in a positive form and negated form, so it's not a pure literal. Likewise, Q occurs in both positive and negated form, so that's not a pure literal. And also R occurs in both positive and negated form, so that's not a pure literal. So we have no pure literals. So the next thing the DPLL algorithm does, it's failed on the first two steps. It hasn't found a pure literal. It hasn't found a it didn't find a unit clause. It also didn't find a pure literal. So the next thing it does is it chooses some literal from the clause. So we might as well start with the, well, quite often you would start with the first one, but actually for the purposes of illustrating the algorithm, let's start with R, because that gives us an interesting route through the algorithm. So it doesn't matter which, it's just some arbitrary choice of literal from within the clause, but in an implementation you would quite naturally go for the first one. Never mind, we're going to start with R, and what we do is we then add R as a unit clause to the conjunction. So let me try and rub off this square bracket and see what happens. That seems okay. Get that dot to go as well. So I got rid of the round brackets as well by mistake, so let's put that back. And we're adding R as a unit clause. That's an R. Okay, so we've added this unit clause, so we can now start the process of running the algorithm again. And so we start with the same first step that we considered the first time, and the first step says, do we have any unit clauses? That's, as I said before, any clause that contains only one literal. Well, indeed, we do have a unit clause. It's this one. It contains just the literal R. So what you do when you find a unit clause is we're going to keep track of the current valuation that we've got. So we make R true. So I'm just going to write R here in the current valuation of truth values to propositional variables. And then, having chosen R, we simplify the conjunctive normal form in the following way. So what we do is we simplify it to an equivalent formula, still in conjunctive normal form, that's equivalent on the assumption that R is true. So if R is true, that's why I've put it in the assignment, we're assuming that R is true. If R is true, then any clause that contains R in an unnegated form, so without a negation, is of course true because it's a disjunction of something with true. So this is true, so we can just omit it. Let's get rid of it from the conjunction because we know this part's true. We don't have anything to, any more information to get about this. We've satisfied this one of the clauses. And also, for any situation in which we've got the negation of R, any clause in which the negation of R appears, well, the negation of R is false, so we're trying to satisfy this clause. This is false, so it means we need to satisfy one of the other literals in the clause. So in this case, we need to satisfy not Q, and in this case, well, we can't satisfy not R because we've made that false. So we try to satisfy not P or Q. That means we go through the following manipulation. So actually what we do is the following, that we write down the clauses again, only if the clause contains the literal we selected, which is R, in the same orientation, so this is positive R, doesn't have a negation, this is a positive R, then we simply remove the clause from the conjunctive normal form. If the clause contains R in negated form, then we keep the clause, but we remove the negated literal, the negated literal from the clause. So that's in general if the clause contains a literal with the same variable but in the opposite orientation to the one we've chosen. So if we'd chosen not R here, we would still keep the clauses that mention R, but we would remove R from those clauses. Here we've chosen R, not R, so we keep the clauses that mention not R, but we remove not R from those clauses. So then we get P or Q, that's unchanged because there was no R or not R in it. And, well, this one we remove because we've already satisfied it. This is a clause containing not R, so we keep the clause, but we remove not R from it. So we just get not Q. And this one here, again, contains not R, so we keep the clause, but remove not R from the clause, so we get not P or Q. And here we have the unit clause that started us off. This contains R in positive form, so we just remove the clause completely as we did with this one. So we're left with this, and we've still got our truth assignment. We're going to propagate this down. We've assumed that R is true. Those of you who've been thinking about how to satisfy this formula might be thinking now, but actually we can't satisfy this formula with R being true. And that's indeed the case. We can't satisfy the formula if R is true. So actually we made a poor choice, if you like, of the literal to consider at the start of the algorithm because we're assuming that R is true and seeing what will happen from it. But the point of the algorithm in difficult cases is that it's very hard to tell whether a particular choice for a variable, whether you should choose it to be true or false. That's very hard to tell because that's the difficulty of the set solving problem essentially. So the point of the algorithm is providing us a way of testing whether we can make R true. We're going to try to make R true and see what happens. Eventually we're going to find that we get to a problem. At that point we know we need to backtrack and make a different choice. Okay, so let's proceed with the algorithm from here. We were dealing with unit clauses. Once you've dealt with one unit clause, you carry on dealing with unit clauses until there are no unit clauses left. So once again, we look for a unit clause here, and indeed we have one. So remember, a unit clause was, let me get rid of that. A unit clause was a clause that contains only one literal. Not Q is a unit clause. So we'll take that and we add to our truth value assignment not Q, which means that what we're doing is we're assigning Q the value false. And once again, we go through the same simplification process that we had last time. So now we are going to remove clauses that contain not Q, which in this case is just the unit clause. And from other clauses, we're going to keep the clauses but remove, so the other clauses, we keep the clauses, but if they contain Q, then we remove Q from the clause. So when we do that, we get, well, we keep the first clause because it does not contain not Q, but it does contain Q, so we remove Q from it. So we have P, and we remove this clause because it contains not Q, and the last clause, we keep the clause because it does not contain not Q, but it does contain Q, so we remove Q from the clause. So we get P and not P. Of course, we can see immediately that this is a false formula, so we should perhaps stop at this point. But normally one implements the stopping at this point in a way that is more natural algorithmically, which is to just carry on with the same process, and we'll get and we'll see we get to a contradiction with truth values in a moment. So once again, we select a unit clause because we're still dealing with unit clauses. And in this case, well, there are two. We could either take P or not P, it doesn't really matter. So let's take P because it's the first one occurring. So we add P to our truth assignment. And we just deal with it the same way as before. So we omit any clause that contains P. So we drop this whole clause. We keep any clause that does not contain P. So that does not contain P in its positive form. So that's this one. But it does contain P in the negative form. So we remove not P from the clause. So we get this. So what we view this is a formula in conjunctive normal form, which is the singleton conjunction of with a single clause in it, and that is the empty clause. Now the empty clause is the disjunction of nothing, which, as I mentioned in the lecture last week, the disjunction of nothing is considered as false. So this is a non-empty conjunctive normal form that contains the empty clause, and that empty clause is false. So this is false because it contains the empty clause. So that's the open and closed curly brackets, round brackets. So false because it contains open and close curly brackets. So what do we do? Well, false means we've got ourselves this truth assignment so far, but it's not a good one because with that truth assignment we got to false. So something went wrong along the way. Can we conclude that the formula is not satisfiable? Well, no, because at one point we made a choice that was not forced upon us, which was right at the very start when we chose the propositional, when we chose the literal R from the conjunctive normal form. So we backtrack to that point, which means we remove all the subsequent assignments to truth values to propositional atoms. So all subsequent truth value assignments to variables that we made after R, and we also removed the one to R itself. So actually in this case we're backtracking and we're going back to the empty evaluation that we haven't made any truth value assignments to the variables. But normally you backtrack just as far as you have to the last point where you had a choice of what? Where you had a choice, you made some choice of a literal from the conjunctive normal form. And what you do now is you choose the negation of the literal that you chose before. So before we chose R, this time we're going to choose not R. So that means our formula then becomes P or Q. So we're going right back to the top line. We're going to write everything out again, not P or R, not Q or not R, and not P or Q or not R, and now it's the unit clause that contains not R rather than R, and we'll add not R into the assignment. Sorry, that's an R, not very easy to read, but not, that says not R. So one thing to say is that we're choosing the negation now of a clause that we, the negation of a literal that we'd previously taken from the conjunctive normal form. I'm just trying to find my, okay, I was just trying to find my pen there. It's actually guaranteed that this negation will also appear in this negated version of the literal will also appear in the conjunctive normal form, because if it didn't, R would have been, in the previous case, what's called a pure literal. So I think I said that already, but a pure literal is a literal that occurs only positively or only negatively in the formula, and all such literals would have been removed. There weren't any in our case, but they would have been removed at an earlier stage. So because R could not, because the original literal R we chose cannot be a pure literal, it has to occur in both positive and negated form. We chose the positive form, now we're choosing the negated form, and we're guaranteed that such a negated form will exist. So not R did occur in the original formula in negated form. Okay, we now carry on with the algorithm. So again, we look for a unit clause. Sorry, I shouldn't really have put the not R here because I've added it to the formula here. Now we take the unit clause, we make not R true, so that is we make R false, and we proceed as before. So again, we drop all clauses that mention not R, and we keep all other clauses, but if any of them mention R, we omit R from the clause. So we see that leaves us with actually very little in this case. We get P or Q, because that clause does not contain R or not R. The next clause contains R, so we keep it, but we drop the R, so we contain not P. And this clause contains not R, so we remove it. This clause contains not R, so we remove it. This clause contains not R, so we remove it. So we're actually done. So we can just go here and close. Whoops, that's, ooh. Try again. Right, that's the end of the square brackets. Okay, here we again have a unit clause. It contains not P, so we add not P to our assignment, and we deal with it as before. So we remove any clause that contains not P. That's what that one. We keep all other clauses, but if they contain P, we omit P from the clause. So we just get Q. And now again we have a unit clause. Its truth value is Q. Sorry, its unit. The literal it contains is Q. That means we make Q true. Oh, I don't know what's happening there. Try again. We make Q true, and again we deal with it in the same way. So we omit any clauses that contain Q. All other clauses we would keep, but there aren't any. So we omit the clause that contains true, and here we get something subtly different from what we got here. This was the conjunction that has one formula in it, one clause in it, and that is the empty clause. This is instead the empty disjunction. It has no clauses in it. The empty disjunction is true, as we discussed last week. So that means with this assignment, R is false, not R is true, so R is false. Not P is true, so P is false. Q is true. With this assignment, the original formula is satisfiable. So the algorithm returns, at this point, let's draw a line down here, so the algorithm returns sat, or yes if you like, meaning the formula is satisfiable with satisfying assignment. Let's put it in alphabetical order, which would often variables are just numbers, so alphabetical order would be, often you list the variables in order, it doesn't really matter. So not P, so that means P is false, Q is true, and R is false. Okay, so let's put a square at the end because that is the end of illustrating the execution of the algorithm. We'll give ourselves a fresh sheet of paper now. And or rather a fresh board. And what I want to consider is, so that was a particular example of running the algorithm. So now I want to consider how we run the algorithm in general. So the general DPLL algorithm works as follows. One part of it was not illustrated in the above, and that was how we deal with these pure literals. So let's write the DPLL algorithm. DPLL algorithm. And it has three main steps to it, the way I like to write it. So the first step is to repeat the process of dealing with unit clauses and pure literals. The first step is repeat the following. So what we look for is, let's give ourselves a bullet point for this step. So we find any unit clause in phi. So unit clause is, as we've said several times, a clause that consists of a single literal. This is an L for literal. Looks like an E, but it's actually supposed to be an L. So it contains a single literal, so that's why I'm putting the round brackets around it. It's a clause with just a single thing in it. So in the conjunctive normal form phi, or, so we find any unit clause, or if we can't find the, oops, where did that go? Let's try again. So, or instead of unit clause, we look for a pure literal. That's again a literal. In the conjunctive normal form formula we're dealing with. Phi. So as I said before, a pure literal is, so the pure literal L is a pure literal if the literal L occurs in phi somewhere in one of the clauses we have an L, but we don't have the negation of L anywhere in phi. So in none of the clauses does not L appear in phi. And then once we've done that, we change the formula phi we're dealing with by reassigning it. So let's use the colon equals that old programming languages used to use when you're assigning a new value to a variable. So we're updating the variable phi, which is the variable for our conjunctive normal form. We're updating that phi with a new value, and that's the new value is what we get when we simplify phi according to the new literal. Now this simplification step, this is the step where we remove, by the literal L, this is the step where we remove any clause that contains the literal L, and we keep all other clauses, but if any of them contain not L, we omit not L from the clause. And when we simplified phi by L, so that's a simpler formula that's equivalent to the original phi, assuming the literal L is true, and our valuation, because we're keeping a valuation as we go along of truth values of literals that tell us what truth values we're assigning to variables, and our valuation becomes the previous valuation, and we simply add L to it. So it's like a list of literals, each for a distinct variable, and we're adding L to that, which is saying we're making the literal L true in our valuation. And we repeat this process until we're in such a situation that the formula phi contains no more unit clauses and no more literals. So we repeat that until there are no more unit clauses ooh, dearie me. Unit clauses or pure literals. When we get to that situation that we don't have any more unit clauses or pure literals to deal with, we go on to the second step of the algorithm. So let's go to a new page for the second step. Maybe I can just keep the pages on the left there. So the second step. So now we don't have any unit clauses and we don't have any pure literals. So let's look to see what we've got. So in some cases, things are very simple. So if phi is the empty conjunctive normal form, so it's the empty conjunction with no clauses in it, then, well, as I've already said, that means phi is true. And so our current valuation has made the original formula true, So then we're done. So we stop, and we return. Let's say we return sat or yes to say it is satisfiable, and we also return the valuation that we've got, which is the satisfying assignment for the variables. So that's one case. Another simple case is if one of the clauses inside the conjunctive normal form is empty, then that clause is false, and any conjunction of things, of formulas where one of the formulas is false, is also false. So that means that current satisfying assignment or partial assignment, we might not have assigned values to all variables, but it's not going to work. We've discovered that it will not make the formula satisfiable. So in that case, we're going to need to deal with that. So in that case, we say if the empty clause is a clause in phi, then what do we do? So let's call it fail for the moment. And we'll see how we deal with fail in a moment in the third step. So you can view fail here as the current search branch we're on has failed to work. If we don't have the empty clause in the conjunctive normal form, well, in that case, so this is an else if neither of the two previous situations apply. So otherwise, we choose any literal occurring in phi, L in phi. And what we do is we recursively, oh dear, so we recursively run the algorithm on the formula L, and that's the literal L and phi. Or I might have put the L at the end when I was running through an example. Of course, it doesn't matter which side it goes. We're just adding one more conjunction. Let's maybe put the round brackets in. It's looking very messy because that's a clause. That's a unit clause. Okay, so this is the unit clause containing L. So the point is, when we recursively run the algorithm, this is going to now give us a unit clause to work with, which will be picked up by the unit clause, and that will be added as true to the valuation. So we run that. If it succeeds, we're fine. So if we succeed, everything finishes, and the algorithm will stop because we'll have returned something. But if this fails, so this is where we deal with the failure. So if this fails, this is how the backtracking works. So if this fails, then we recursively run the algorithm on, well, so we've tried L being true, so we negate the literal, so not L, so then we try the algorithm on. Oh, that's a phi. Let's make that a bit neater. And if this fails, then the whole program fails. So if we can't find a satisfying solution with L being true, and we also can't find a satisfying solution with L being false, then there is no satisfying solution. So if this fails, then return that the original formula was not satisfiable. So let's say non-sat. It's a non-satisfiable formula. Okay, there are a few things to say about how this algorithm actually works. It's a little bit underspecified, as I've so there are a couple of things that aren't completely clear in the way that I've written it. So the first one is that, so let's write it as an NB for nota bene, or note well. So I'm making the following point about the algorithm, which is that when a recursive call fails, the backtrack is to the most recent available literal choice. So the most recent place that the choice of a literal in part 3 of the algorithm was made. So when a branch fails, or rather when a recursive call, so when a recursive call fails, oh dear. There's this really annoying button on the pen that I keep on accidentally pressing. When a recursive call fails, the algorithm backtracks to the most oh no, here we go again. Oops. Oh dear, this is getting really messy. Let's see if I can So to the most recent choice of literal in step 3. If you implement it in the right way, this will be taken care automatically for you by the programming language. Right, what else is there to say? Well, I suppose I should define, I've said it several times, but I suppose I should, strictly speaking, define the simplification step in general. So let's say that simplify, so if we simplify a conjunctive normal form, so that's like a conjunction of clauses, C1 through to CK. We simplify that by a chosen literal L. Then what we do is we form a new conjunctive normal form, a new CNF, from the original one, from the original but we do the following. We drop all clauses that contain the literal L in the same orientation. That is, if L is a positive literal, the clause contains the positive literal L, and if L is a negative literal, that's a negated variable, then the clause contains the negated literal L. So we drop all clauses containing the literal L in the same orientation. I'll just write containing L because I've said the same orientation clearly several times. So containing, and we retain all other clauses, but in the case that one of the other clauses contains not L, then we omit not L from the clause. We keep the other literals in the clause, but we omit not L. But omit all literals not L. Okay. So I think that is enough said about the details of the algorithm. Let's just go have one more. Let's go to one more page. I just want to tell you one property of the algorithm. So DPLL has a good property, is a complete algorithm. Oh, again, very messy. So for the SAT problem. And what this means is that for any conjunctive normal form, it works in the following sense, that if a conjunctive normal form is satisfiable, then, oh, oops. Right, we need, oh dear, let's cancel that. See if I can get rid of this. Oh, that was easy. Right, I think we're going to have to pause the video soon because things are getting a little bit out of hand. But anyway, if phi is satisfiable, then the DPLL algorithm will return, so it finds a satisfying assignment if, on the other hand, phi is not satisfiable, which is, of course, the only other case, it's not sat, then DPLL will tell us that. It says so, whatever the case, DPLL will give us the information we need, either a satisfying assignment if the formula is satisfiable, or it will tell us that the formula is not satisfiable. Of course, the only problem is, and it's a very big problem, that you might have to wait a very, very long time for an answer. Nonetheless, what I want to talk about in the next part is about how one can implement the algorithm, and also how things can work a bit better than this in practice. But I think now's a good point to have a break, so I'm going to stop this video, and we will resume in 15 minutes time by the clock on the back wall. Okay, so I'm going to pause this video now.